So problem number 1, you're given a graph of f prime, and you're told that there are horizontal tangent lines where there appear to be horizontal tangent lines. And you're told a couple of pieces of information as well. The part A says to find all values of x in the open interval for which the function has a local minimum. So keep in mind a local minimum happens when the derivative goes from negative to positive, and this is the graph of the derivative. So if I were looking at this and I made a sign line for it, you see it equals 0 at 1, at 4, and at 6. So if I put those numbers on my number line, and we're only told about the graph from 0 to 8, we don't really know anything else outside of that. So I'll put that on the end of my number line. So in between 0 and 1, you see it's above the x-axis, so it's positive. And between 1 and 4, it's also above, so it's positive. Between 4 and 6, it's below, so it's negative. And then 6 to 8, it's above, so positive. So that's the derivative. So the original function then would be increasing, increasing, decreasing, increasing. So you can see that there's a local min at x equals 6 because the derivative goes from negative to positive. Now you can say negative to the left, positive to the right, that's fine too. So part C says on what open intervals contained in 0 to 8 is the graph both concave down and increasing? Well, we already know where it's increasing. We saw that from the sign line we just made. So if we make a sign line for the second derivative now, we'll be able to find out where it's concave down. So this is the graph of the derivative. So keep in mind, second derivative would be slopes on this graph. So we would be looking for places where the slopes change. So the slopes change at 1, at 3, and at 5. So when I put those down, I'm looking at the slopes on this graph to see if the second derivative of the original function is positive or negative. So the slopes start out negative, and then the slopes are positive, and then the slopes are negative, and the slopes are positive again. So that would be concave down, concave up, concave down, and concave up in the original graph. And the problem said we want concave down and increasing. So it's concave down from 0 to 1, and it's also increasing from 0 to 1. So that's part of my answer. Now at 0, it's both concave down because the slope is negative and increasing because the y value is above the x-axis, so you would include 0. However, at 1, it's not increasing or decreasing because the slope is actually 0 there, so I'm not going to include it. And then concave down again between 3 and 5, but you notice it's increasing only like between 3 and 4. So 3 to 4, and I would not include 3 because it's not concave down there, and I would not include 4 because it's neither increasing or decreasing there. So part D, you're given this third function, g of x, second function, I guess. And you're told that it's f of x cubed. You're told f of 3 is negative 5/2, and to find the slope of the line tangent to the graph of g. So if you want the slope tangent to g, you want to find g prime, which would require the chain rule. And when you do the chain rule, you could write it all out if you'd like, but it would look like that. So I want to find the slope at 3. So I plug in 3 for all the x's. You're told that f of 3 is negative 5/2. And then f prime of 3 you can get from the graph because we're given the graph of f prime, and at 3, that value is 4. So that basically gives you 3 times 25 force times 4, which is 75. Next problem. You're given a chart that measures the rate of change of the radius of a balloon, and you're given lots of information in the problem about the balloon. So part A says estimate the radius of the balloon when t is 5.4 using a tangent line approximation at t equals 5. So we want to build a tangent line at t equals 5. And t is my independent variable here, so it's like the x. And then r is my dependent. So you're told at time 5 that the radius is 30 feet. So that's like getting the y value at the point of tangency. And then we need the derivative at time 5. Well, the chart tells you the derivative of r. And time 5, that derivative is 2. So the slope of the tangent line is 2. So my tangent line's equation, and I'm going to write in terms of r and t rather than y and x, just to keep things less confusing, would be r minus 30 equals 2 times t minus 5. So that's the tangent line, and they wanted you to use that to approximate t 5.4. So I'm going to move the 30 over, and I'm going to plug in 5.4 for the t, and that would give me 30.8, and the units are feet. Then the problem says, is your estimate greater or less than the true value? Well, remember, tangent lines are greater or less than depending on concavity. If it's concave down, the tangent line's above. If it's concave up, the tangent line is below. So you're told in the problem that the graph is concave down. That means whatever tangent line we've drawn is going to be above the graph, and therefore it overestimates. It's greater than. And that's because the graph is concave down. Now, part B. It says find the rate of change of the volume of the balloon with respect to time when t equals 5. So that's a related rate question. So you're given the equation for the volume of a sphere. And we want to take the derivative with respect to time on both sides, which require the chain rule. Now, you can switch that over to the Newton notation. For time's sake, I'm going to do it without doing that. And then you want to find dv dt when t is 5. We need r dt at 5, and we need r at 5. Well, both of those, as we discussed in part A, r is 30 when t is 5, and r prime is 2 when t is 5. So r is 30 when t is 5. And dr dt is 2 when t is 5. Now, if I were keeping up with the units, the 30 is going to be in feet, and the 2 is going to be in feet per minute. So when I multiply that out, let's see, that'd be 900 times 8 is 7,200 pi, and it would be in cubic feet per minute. Okay, next problem. The functions f and g, you're given information about them in a chart, and you're asked questions about those functions. So part A says, explain why there must be a value of r such that h of r, and h of course is this thing, is -5. So really, so you're told about an interval between 1 and 3, so you kind of want to see what happens at 1 and 3 and see if you can draw conclusions from there. So if I were to find h of 1, h of 1 would be plug in 1 for the x. And then I can use the chart to find out what this value is. So g of 1 is 2. And then f of 2 is 9. So h of 1 is 3. I'm going to do the same thing for 3. Plug in 3. g of 3 is 4, and f of 4 is -1. So h of 3 is -7. Now you were told in the original problem that the functions are differentiable, which basically means that it's continuous everywhere, right? And it goes from a y value of 3 to a y value of -7. Then, you know, because the function is continuous, then by the intermediate value theorem, every y value in between 3 and -7 is hit by some point. So the function h is continuous, or differentiable, you could say differentiable, because that implies continuous. So by the intermediate value theorem, R must exist. There must be some point in that interval that gives you a y value of -5. So for part B, it says, explain why there must be a value such that h prime is -5. So this has a lot to do with an interval and a slope in the interval equaling something, and that's more like the mean value theorem. So if I looked at the mean value theorem and actually got the AROC over the interval, that would be h of 3 minus h of 1 over 3 minus 1. And we found from the first part, h of 3 was -7 and h of 1 was 3. So that gives you -10 over 2, which is -5. So the mean value, the AROC, is -5. So by the mean value theorem, since this function is differentiable, then C must exist. There must exist some C in the interval such that the IROC equals that, and the IROC is that h prime of C.